Thanks for watching. And in this example, we kill two birds with one stone because we practice with both energy methods and Laplace's equation. In particular, in this first part, show that if U solves Laplace's equation with zero boundary conditions, then U is the zero function. So once again, what happens here, inside U solves Laplace's equation, and on the boundary, partial omega, we assume U is zero. And what we want to show is that U is actually the zero function. And for this, let's use energy methods. Before we proceed, let me tell you the integration by parts formula that we'll need here. So IBP formula. Namely, in this case, the multivariable integration by parts formula is the integral, in this case, of Laplacian of u times v dx is the same thing as minus integral of the gradient of u dotted with the gradient of v dx over our region, which, by the way, is valid for any function v that is zero on the boundary. So valid for all v such that I think v is zero at the endpoints. So on partial omega. And I know it looks a little bit weird, but it's actually very similar to the one-dimensional formula, because in one dimension, the analog of this would be integral of u double prime of v is minus integral of u prime v prime. So in other words, we're just putting the derivative on the right-hand side, but with an extra minus. So just take a second to compare that. All right, and now we can proceed. So once again, our equation was Laplacian of u equals 0. And the trick is, remember, for energy method, is to multiply by a certain function and then integrate. So in this case, let's multiply the PDE by u itself. So we get Laplacian of u times u equals 0 times u. And then let's integrate over omega. Integral over our domain. This dx is integral over our domain. This dx. Now, the integral of 0 is just 0 in this case. And for this thing, we just integrate by parts. But the integral from over omega of Laplacian of u times u dx. So here, you just integrate by parts. So you use the formula I wrote down before, but in this case with v equals u. So with v equals u, which again is okay since u is 0 on the boundary. So here's where we use the boundary condition. On the boundary, and then what you end up getting is simply minus integral over omega of the gradient of u dotted with the gradient of u dx. And remember, whenever you dot a vector with itself, it gives you the length squared. So this is just a general property of vectors, and so you're just left with the length of the gradient of u squared with a minus. And so combining everything, we get that this quantity, which is minus gradient squared, equals 0 in the end. And so what we end up getting is the following. And so we get that minus the integral of the length of the gradient squared dx is 0, and the 0 on the right hand side, we end up getting that the integral of the length of the gradient squared is 0. Now, what does that mean? Just as usual, notice this is a positive quantity because it's length squared. So we're saying that the area under this positive function is 0. So the only way this can happen is if that quantity itself is 0. So this tells you that the length of the gradient squared is 0 in our region. And so the length of the gradient is 0 in our region. Now, if the length of a vector is 0, that vector itself is 0. So the gradient of u is the 0 vector here in our domain. And well, if the derivative of a function is 0, the function is constant. Same thing here. If the gradient of u is 0, we knew that u is a constant in this case. So therefore, u is equal to a constant in our region. And now remember what we have so far. So this is our region omega. We know that u is a constant inside it, but also u is 0 on the boundary. So the only way that u can be a constant and be 0 on the boundary and technically be continuous is if u is 0. So since u is 0 on the boundary, we get that c is 0, and so u is in fact 0 in our region. And then we're done. So notice it is quite similar to energy methods in one dimension in the sense that we multiply by a function, we integrate by parts, we find the derivative of the function is 0, and we conclude that in that case using the boundary conditions that u is 0. Now, similar to before, we can also use that to prove uniqueness. So in the second part of that problem, we'll show uniqueness, namely show that there is at most one solution, to the PDE. So not Laplace's equation, but its relative, Poisson's equation, Laplacian of u equals f in your region, and then u equals g on the boundary. So in this course, the main way to prove uniqueness is to assume there are two solutions, subtract them, and then show that the difference is 0. So suppose u and v solve the PDE and let w be u minus v. Then let's find a PDE for w. So Laplacian of w is Laplace of u minus v, and that's just Laplace of u minus Laplace of v. But once again, u and v solve that PDE. So it's f minus f, which is 0. So that's in your region. And on the boundary, we have w is u minus v. But on the boundary, u and v both have value g. So it's g minus g. And so this is 0 on the boundary. And so what do we conclude? Well, we conclude that w solves the following PDE. So therefore, w solves. So Laplacian of w equals 0 in your region, and w is 0 on the boundary. But this is precisely the equation we've dealt with in the first part, and we conclude that in that case, W is 0. So by A, we get that W is 0, and therefore, remember W was U minus V is 0, and in the end, we actually conclude that U equals V, just as we wanted. So again, this is a very typical uniqueness proof after energy methods. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.